Okay, our job is to integrate x times the tangent squared on x. I put the dot there to help you recognize that this should be an integration by parts question. It's a definite integral, so we'll later worry about the bounds. Let's focus our attention on integrating x times tan squared of x. So it's integration by parts. We get to choose u and choose dv. Use the hierarchy, the mnemonic, that helps you figure out what to choose u to be. If there's a log function, you should choose u to be the log. If there's an inverse trig function, you should let u be the inverse trig in the absence of a log. In the absence of an inverse trig and a log, you should let u be the algebraic function. Algebraic is a polynomial, or it may be even a root function, and so that's where we start. We should let u be equal to x, leaving dv to be tan squared of x dx. So then our job is to integrate the dv and differentiate the u. Why do we differentiate the u? So that we can get du. Why do we integrate the dv? So that we can get v. Because the parts involve the u and the v and the du. And so we need these guys. So we go get them. What is the derivative of u? What is du? It's x's derivative, which is 1. What is the integral of tangent squared? What function has tangent squared as its derivative? Eek. I don't know. All right, but you have help. There is an identity on tangent squared that you can use to help you integrate it. It's the Pythagorean identity. 1 plus the tangent squared is equal to the secant squared. So that you can solve for tangent squared and get the tangent squared is secant squared minus 1. Why is that helpful? Because you know what function has secant squared as its derivative, and you know what function has minus 1 as its derivative. You can take this antiderivative here. You can integrate. And so the value of v would be tangent of x. That's what secant squared is. That's who has secant squared as its derivative. And x. So tangent x minus x is what v is. Okay, we'll put these pieces of the puzzle back together on the next slide, and we'll be able to execute the integral. We have all the players there. Our job is to put the pieces of the puzzle together. We have u and v to multiply with no integral. And then we have v and du to multiply. And we integrate that product with a minus. uv minus the integral of v du. That's what the new integral, that's what your trade-in is. Your old integral is equal to that. All right, here we go. So we go x times tan x minus x, and then we go tan x minus x times 1, or times dx. 1 dx. And we minus that integral there. So we did great. So what we're going to do next is distribute the minus across, and then maybe separate into 2 separate integrals. We have the tangent of x, and then we have just x. But the minus and the minus gives us a plus. Now, hopefully, you know the integral of tangent. Okay? If you don't, we can work it out quickly here. The integral of tangent is going to be done by trading in it for sine over cosine and doing a u sub. We let u be equal to cosine x because du is negative sine x dx. And so we can replace sine x dx with negative 1 times du. And then that'll be on top of u, and we integrate that, and we get negative natural log of u. So we get negative the natural log, officially absolute value, of the cosine of x. But what we can do with that is bring up that negative 1 as the exponent. And then the cosine of x, who's raised to the negative 1, is like having 1 over cosine x. And we're going to call that secant x. So there we have it. The integral of tangent x is equal to the natural log of secant x plus a c. But here we're going to just hold off on that and later go back and plug in the bounds. Okay, great. You have to integrate x. Don't forget that part too. It's x squared over 2. We have our antiderivative in hand. We treated this as if it was an indefinite integral, and now we want to go back and consider these bounds. Using the fundamental theorem of calculus here, we're going to go back and consider the bounds. So we want to then plug a pi over 3 in and plug a 0 in. Every place we see an x, we'll put a pi over 3. Every place we see an x, we'll put a 0. Let's do that on the next slide. So pi over 3 times the tangent of pi over 3 minus pi over 3 quantity, natural log of the secant of pi over 3, and then we got to pi over 3 and square it, divide by 2. That's all the upper limit. Plug it in 0. Well, 0 times anything is 0, so we'll end up with a natural log of the secant of 0. We're going to find out that zero's out. 0 squared over 2, that's 0. And so what's going to happen is the secant of 0 is 1. The secant of 0 is 1 over the cosine of 0. And the cosine of 0 is 1. So the secant of 0 is also 1. But the natural log of 1 is 0. And so the entire lower limit zeroes out. I'm just dealing with this upper limit. Okay? There's the secant of pi over 3. Okay? And that'll be 1 over the cosine of pi over 3. And the cosine of pi over 3 is a half. So 1 over a half is a 2. So that guy would be a 2. The tangent of pi over 3 is going to be the sine of pi over 3 over the cosine of pi over 3. Okay, and that is going to be root 3 over 2 divided by 1 over 2. So it's going to be times that 2. And so it's going to be root 3. And I think we're ready. There'll be distributing going on here. And so we'll distribute the pi over 3 across. And then this is going to be square the numerator, square the denominator. That'll be pi squared over 9. But then that's all over 2. That's how we get pi squared over 18. Here comes another pi squared from this distribution here. It'll be pi squared over 9. So yeah, the signs are all correct there. And we can then just put these pi squared terms together. Pi squared over 18 minus pi squared over 9 times in by 2 here. We'll have 2 pi squared negative. And then we add on pi squared to that. So it's going to end up as minus pi squared over 18. Minus the natural log of 2, and then this strange pi root 3 over 3 as our answer. Okay, so if you don't know how to integrate something, maybe there's a trig identity that can help you out. Okay, great.